Hey everyone. Okay, before I get started, let me just test the equipment, make sure everything is working properly. I feel that each day I do this, I get more comfortable with getting all the setup going and everything. I've switched around my monitor, so I am gonna, when I'm writing, I'm gonna lean more toward the camera instead of away from the camera. And then, yeah, let's see what else. Make sure everything's working. I have a separate computer running over here, so that way, if I'm watching myself, I can check. So let's see what I got going on here. Okay, test, test, test. Can I hear myself? I can't hear myself. Let me figure out if I got myself muted or what. Could be that my wire. That's what it is. Okay, there's the wire. Okay, it's working fine. Okay, so I test, 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 test. Okay, let's make sure. Okay, so the audio adjusts pretty well. All right, looks like I am good to go then. I'm gonna mute myself on here, but I'm still gonna watch in case they screw up the screen setup. Okay. All right, and just gonna drop a quick hi everyone in the chat. Okay. So yeah, just the usual thing. This is a parasocial stream, so I'm gonna proceed with the program I have laid out. If you wish to make any specific requests, you can do that. Just you drop it in the chat. But if you want me to display it or react to it, primarily you send me a your message with a $5 Venmo. And because it's a parasocial stream, like people are able to take control of the stream, so to speak, and affect the direction it goes, the stuff I cover and so forth. And of course, anything that's profanity or something like that, I would have to block that or, not show that. But primarily, I'm focusing on math right now. So I am doing this as much for myself as anyone else. So that in that case, I'm gonna do that in that vein, so to speak. All right. So I'm gonna continue from where I left off last time with the math. And let's see here. Okay. The general rules apply so that I'm going to do these equations. If I get it wrong, you'll see me get it wrong. So don't think of me as a teacher, think of me as a classmate, someone maybe that's a year ahead. So in that case, it'll give you some idea. And I'm going to probably get stuck sooner or later. So expect that. That happens. All right. Let me just go. Right, this is fine. And then, all right. So we finished off last time section A. So we're continuing with question number 17. Okay, 17. All right. And let me put this on here. Go and okay. 17. Write each of the following sets in set builder notation. All right. So what they're doing here is they're giving us the set, and this is written in. So they're giving us the set, and then we have to write it in set builder notation. So we have 2, 4, 8. This is gonna get fun real fast. 264. Now, hopefully you are detecting a pattern already. Now, so we see this 2, 4, 8, 16, 32, 64. Right away, we can see that it doubles, right? What can we do to apply to this to bring a little bit more order to it? That's the question. So we look at it. All right. So what do we know? If this is going to be like, if we take one number, right? Just one number, what can we do? What action can we take on it that will take that number and turn it into all of those other numbers, right? So let's look at it. Let's say right away I can say analyzing these numbers. The simple thing for me it is 2 to the first power is equal to 2. All right. 2 to the second power is equal to 4. 2 to the third power equals to 8. 2 to the fourth power. And so right away I'm seeing so and in that case, so we know that the numbers goes up and it starts at 1, so it's a counting number, right? And it's a natural number. It doesn't start at 0, and these are all whole numbers, and as far as we can tell with dot dot dot, in other words, that says and so forth, the pattern will hold forever. So, here's what we can do. We're going to say that this we're dealing with whole numbers. So we're going to use natural numbers, natural whole numbers, counting numbers, and the natural set, I'm just going to give it away right here. 2, 3, 4, dot, dot, dot. This is our natural. So right away, we know that this is going to be a natural set. So here's what we're going to do. We're going to say x 2. Here I'm going to write this a couple of ways. I'm probably going to mess this up initially, but right now we're not. Let me back this up for a second. I made a mistake. Okay. 2 to the x such that x contains the natural set. All right, another way to write it. 2 to the x such that x contains the natural sets. Another way we can write it is we can say x contains the natural sets such that 2 to the x. Right, now we're gonna look at that, but essentially this is what we're doing here. This should give us the pattern. We go back in the book. Let me look at it. 17. Yeah, it's 2 to the x, such that x contains the natural numbers. So yeah. So basically, yeah, that's it. That's the answer. Specifically, they wrote it in this. Let me see here. 17. So they're using this such that this is the version that they're using right here. This is specifically exactly as it's written in the book, but you're getting the same results. So sometimes you change the orders and such that, but it's still saying the same thing. So that was good. Let's do a file new. Save. Okay, good. Now, let's continue with 19. All right. This is a fun section. All right, so I'm going to start writing right away. You have to, first of all, you're looking at this thing. You have to decide which domain this is in. And looking at this, it has, these are all whole numbers, right? So this is not in the reals. Although reals are in the whole numbers, but the specific set is more constrained than the reals. There are no fractions here, no irrationals. So, what we do know right here is this is going to be in Zahlen or Z. That's the German word, Zahlen, meaning that numbers. So that's the set that we're working with. The domain is Zahlen or Z or integers specifically. So this is integers. So it goes positives and negatives. Let's say, what can we tell right away? What number applies to everything here? This is clearly a multiple of 3 of some form. So what if we do this? We say, let's see here. 3 to the x such that x contains integers. Why don't we just do that? All right, so if you look at that, let's look at our numbers. 3 times 0, 0. 3 times 1. Now, again, we are trying to recreate the pattern up here. We want to create this pattern, right? But how would we do that? Well, again, this set right here, for convenience sake, I'm just going to write it real quick. 2, negative 1, 0, 1, 2. Okay. Now, let's just plop this in real quick. So we can take the 0, 3 times 0, and we get our 0 right here, right? Perfect. Back up. Okay, now what if we pop the negative 1? Okay, then there's our negative 3. Perfect. All right. If we pop the 1, there's our 3. Okay. So we are recreating the set. That should be fine. Let's take a look at the book. 19, 3 to the x, such that x contains the integer set. Yep. That's exactly what the book said. All right. File new. Done with that one. Don't save. All right. 21. All right. Let's see here. 0, 1, 4, 9. This is 16, 25. Again, we want to decompose these numbers and understand what is happening to them. And the way to do that, you have to put pen to paper. You have to try things, right? So it starts with 0. So, by the way, we could put boundaries on our numbers. For instance, we can say something like, let's see here. We can say integers. Let's see here. X contains integers such that x is, say, we're going to say greater than 1. So in that case, it's going to be, the numbers would be, it would be 2, 3, 4, 5. So that's how you can also get that. So you don't necessarily have to take the whole set. Just get rid of this. So that's another idea that you should just keep that in the back of your head. But the thing with math is that it's meant to be, don't put in more work than necessary. That's the idea. If you can get the simplest answer, that's usually the best answer. But looking at this thing, I'm seeing powers or something like that, right? So let's see here. Right away, my instinct says it's powers. If we go x to the 0 equals 0, let's see here. No. Actually, let me think about this for a minute. So the power is, if we take the, well, actually, let's decompose these. So this is going to be 0. Let's see, this is 1. We'll come back to a minute. This is 2 squared. This is 3 squared. This is 4 squared. This is 5 squared. This is 6 squared. Right? Okay. So then, now the 0, we could also say this. Okay, so we do need to get a 0. So we cannot use our natural numbers because we need the 0. So this has to be integers. So we're going to need our Zahlen here. All right. But like I just said earlier, I gave it away without even thinking about it. So what we're going to do is we're going to try doing this. So we're going to say, so I might get this wrong, actually. So these are all powers of 2, right? 1 is, so this is going to be 1 to the power of 2 is also 1, and 0 squared is also is going to be 0. So then we can say that we're going to say x squared such that, let's see here, x is greater, here. I'm probably going to get this wrong, but I mean, I'm probably going to write it wrong initially, but what I'm saying is correct. X has to be, let's just say here, we're going to say we need to have this, we're going to say greater than or equal to 0. X is greater than or equal to 0. And let's see here. Comma x contains the integer set. This is what I'm going to say. So we're going to say x squared such that x is greater than 0 and x contains the integer set. Now, I suspect that I wrote it a little bit in a funky way. Not strictly ballroom. Okay. Oh my God. Oh my God. How could I be so dumb? All right. Look. Here's the thing. If we take -1 and square it, we're going to get 1. -2 squared, we're going to get 2. So we really don't need me saying x is greater than 0. I mean, yeah, it'll still get the same answer, but the book is simpler, right? Such that x contains our integer set. So that's it. Because even though the numbers double up, it's still the same set. It is still, we're still getting the same results. So x squared such that x contains the integer set. And yeah, whether it's a -2 or a 2 squared, you're going to get 4. So yeah, that's fine. It's going to be 4 there. All right, so that's fine. Yeah, I just went a little overboard, but the idea, what I said will work. You'll get the same result. It was just a little unnecessary. Let's go new. All right. So, okay, let's go to 23. But this one here is clearly constrained. 3, 4, 5, 6, 7, 8. So we're going to say x is greater than or equal to 3 and less than or equal to 8, such that x contains naturals. That's pretty straightforward. If x is greater than or equal to 3 and less than or equal to 8, and x contains the natural set, then that's what you're going to get. Although we could have used a different set. We could have used integer set. Either one would have worked. 20, let's see here. Yep. X contains naturals such that x is, greater than or equal to 3 or less than or equal to 8. Now, in the book, they wrote it like this, which is, again, the same thing. They go back and forth in this. Again, they want to get you used to the idea that you can go back and forth in the writing, because sometimes, you know, it's like you get so used to writing it. All right, and you're going to be like, oh, my goodness. But anyway, yeah. So I just wrote it in the other order. It's the same answer. The book goes back and forth and went into the way it answers because they want you to be able to be comfortable with reading it either way. All right, next. All right, 25. All right, so we're going to say fractions. All right. Okay, now you're going to think, right? You're going to say, all right, we are using the real set, right? Feels like we're using the real set. But are we? Can we get this result but not dip into the reals? Because here's the thing, look. If you look at this thing, this is this set exists in the reals, right? In terms of just the set itself, but to create it, we don't need the reals. So here's a fun fact, right? If we if you take let's see here. Let's say here we're gonna say 2 squared is equal to 4, but 2 to the -2 is the same as 1/4. This is something, if you don't know it, you probably aren't going to get this right away. But essentially, if you are having a power, you're taking some to the power of something, 2 to the -3 is the same thing as an 1/8. So in this case, it's just they're simply applying powers to it. And but in this case, we're still using whole numbers, even though it's creating fractions. They're applying powers. So let's see how we just write this pattern. All we know is that, so this is going to be, let's see here, 2 to the 3rd, -3. So essentially, we're taking the number 2 and x, and we're going to say, yeah, such that x contains integers. And if we did this right, it should be correct. So let's look at that real quick. You should also know this. 2 to the 0 is 1. Anything to the power of 0 is not 0. It's 1. That's important. These three things, these points, this one, and that, well, I guess you already should know that one, but these 2 points, taking a negative power of something creates a fraction, and 2 to the power of 0 is 1. If you know those 2 things, you could easily create this pattern. But let's look at the book just to confirm it. 2 to the n. Now again, so here's what they did. I've been using x. They swapped it to n. That is completely acceptable. Normally, like, there are traditions, like, to make things easier to read, right? So normally when we have stand-ins for a value, we usually use x, y, and z. Also, we could use n and m, if you need it. Depends what you like. Also, I mean, like, and this is why they want you to read. They want you to say, I mean, like they used a and b previously. These things, we can swap things around. Other ones, like, for instance, this is another thing. Some people, right? Remember yesterday I was talking about how a full rotation around a circle, that's going to be 2 pi, right? Well, that's also the equivalent to tau. Tau and 2 pi is the same thing. Some people say, "Oh no, 2 pi is wrong. Oh no, 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 no! It has to be tau." It's the same thing. It's just like some people write that, or we can say half a circle is going to be pi, or we can write half tau, like that. That's fine too. It doesn't matter. Anyway, those are just ways of reading things and understanding, just being comfortable with it. All right, let's continue. All right. And okay, and speaking of pi, I don't know, maybe I'm subconsciously picking up these questions because I was not even seeing that. The next one contains pi. Negative pi. All right, we have pi over 2 negative. All right, we're gonna have to take a minute to think about how they're creating this. Pi over 2. Pi 3 pi over 2. 2 pi 5 pi over 2. All right, so how do we create this pattern? So we need something times pi. All right, let's see here. If we multiply this by, all right, so it keeps adding. There's a fraction going on here. Right, you got to see the fraction. All right, let's pull this out a little bit. So we're gonna say that pi times negative 1/2, that one. Okay, and this one, we're gonna be able to say this, negative 2 times pi, right? This is gonna be 0 over 2. We could say pi, sure, why not? And this will still be 0. And over here, we're gonna say pi over 1/2. And here we're going to say 2. And again, this kind of stuff, you might stare at it, and it's just like the more you work with numbers, you kind of start to get a feel for what's going on, just by combining and taking them apart. And I didn't have any prepared notes. I'm just doing this on the fly. And it's not because I'm smart or anything, because I'm not. I'm a landscaper. But this is the kind of stuff that if you practice enough stuff and you enjoy it, you can see it. Anyway, so look right here. Let's grab a different color here, right? We got this, 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 and this, right? And then, of course, we got our negatives. So what are we dealing with? Clearly, we are dealing with Zahlen, or integers. In that case, what else do we have, right? If we just pull those numbers out, so then we're going to take the negatives out, actually. Pull that out into it like that. So then we have x over times half pi. And then we're going to say such that x contains integers. All right. And that should create that set. All right. Let's take a look here. And again, the way I wrote it here, you can also write it like this. Same thing. Times 1/2 times pi. Or you could also write this, x times pi over 2. it doesn't matter. Same results, or you could also write this like this: x pi over 2, all the same thing. Yeah, let's look at the back of the book here, number 27. So here's what they did here. Again, same thing, only they used k. So they said k pi over 2, and such that k contains integers. I use x, they use k. Doesn't matter. Same thing. All right, good. So, all right, we got through section B. That was great. All right, we got to find. Let's do C as well. Oh, how are we doing on time? Not bad. Take a minute break here. So, a second to rest from talking. So far, so good. The next thing is going to be different. We're dealing with cardinalities. All right. What is the card? I got to refresh on this thing. Cardinalities real quick. Cardinality means the size of the set, right? Okay, yeah, the size of the set. That's what cardinality means. I remembered now. I didn't see it in the book. I just remembered. All right, so we are in 1.1. We're in section C, and then we are number 29. So we're looking for cardinalities. All right, so now, remember when I talked about the absolute value? This is the absolute value bar, right? Well, not anymore, because now this is also the cardinality symbol. All right, so we are looking at the size of the set, and I'll explain what that actually means in a minute. There's a very simple way how to do this. They're going to throw all kinds of ways to try to confuse us, and there's a very, very simple way to find the cardinality. And I'm going to read this for you first once I write it out. All right, so we got this thing going on here, right? So pay close attention. So this right here, that refers to the empty set. So that's a concept. It's not zero. It just means an empty set. It's the equivalent of having a brace like this. So it's a set, but there's nothing in the set. When we talk about sets, I want you to imagine boxes, okay? Boxes. So it's just a box, and you got nothing in the box, right? Nothing. Nothing exists in this box. So, all right. Now, let's talk about the cardinality. These things right here, it looks like absolute value bars. Oh, this means cardinality. Cardinality means size. So how big, how many items are in this box? Now, the way you do this is, here's what you do. You take the outermost brackets, these ones right here, and then you pretend they don't exist, okay? Now, you don't normally just run it like that, but you can if you want, whatever. I mean, you're doing the work. So now we're going to count how many distinct items. When I say distinct, I mean things that have an open curly bracket and a closed curly bracket. All right, that's what we care about. We have, let's see here, we have 1, and then we have 2, and we have this one, which counts as an item, because even though it's an empty set, it's just like the equivalent of a curly brackets, open and closed, right? I said all we care about, we don't care what's in them. Don't get confused by what's in them. See how there's a bunch of stuff in there? Don't care. Not a problem. All you want to know is how many. So we got 3. Cardinality of 3. Let's take a look. 29. Yep. Cardinality of 3. It's good. Problem solved. All right. Let's continue next. All right. So we have 31. All right. And I'm just going to write this out. By the way, I listened to myself when I was working, when I was doing painting earlier today. I really enjoyed yesterday's presentation, even though it's listening to myself. I know, maybe pretentious, but whatever. As long as I'm entertained, that's enough for me. And if anyone else is entertained, that's great too. But this way, at least I have one happy customer. in terms of my presentation in the video here. Here we go. Okay, so let me make sure I wrote this correctly. All right, so let's just do this. We're talking about the cardinality of this set. I'm not going to read out the set because reading it out just will be confusing. But you have to start with the inner. Well, we're going to take the outermost ones. We're going to scratch them, and then we're just going to count this up. So we have this curly brace, right? This is one we care about. All right. So we have open, 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 open. What's the biggest closed one right here? So this one's right here. Now, notice how this thing right here, you have two opens. So then the way you do that is, so we have, right. This, now here's the thing. You can get confused by counting how many you got. But the most important thing is that we know that these two are connected. That we have these two are connected. We know these two are connected. All right. So then we know these two are connected. So then we want the first one that's outside of the ones that I scratched. And there's only one. So the cardinality is 1. There's only one item in this box. All these sub boxes, doesn't matter. Cardinality is 1. Yes, book agrees. All right, good. Let's continue new. All right. 33. Okay, 33. So we have, all right. Integers such that the value of x is less than 10. All right, now he gave us one of the previous type of questions. So let's read it real quick. We want to know, so this is for, there's something going on here, right? But this isn't like the other questions we've answered. It's kind of a combination of the two. They're asking, what is the cardinality of this equation, right? So let's just kind of like think about it. There's two things they want to know. They want to know the size of the amount of items produced of the equation. So the equation is going to spit out distinct objects, and then we want to count up the number of those distinct objects. That's it. So that's the second part. So let's before we could answer that, we have to figure out how many distinct objects exist there, right? So let's forget about the absolute value bars for a minute, and then, or in this case, we refer to them as cardinality bars. We're going to forget about that. Instead, we're just going to read the equation. The set of x containing integers where such that the absolute value of x is less than 10. So, well, we know that 1 through 9 is less than 10. And we're just going to write out the whole set. But we also know that 0 is in an integer set. So, and that's less than 10. We also know that, now notice, there's two types. There is absolute value and there's cardinality bars. So this is meant to throw you off, but we're not going to get thrown off by that. So we're going to use the inner ones as the absolute value bars. So then we know that the absolute value of -1 is 1, and that is less than 10. So perfect. And we also know that -9, the absolute value is 9, and that's also less than 10. So then we know that, first of all, we're going to write up the set, and it's going to be -9, -8, -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, that's our set. Now, these are all distinct objects. Each number is not any other number. So in this case, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, plus 9 plus 1 is 19. So the cardinality right here, the answer to this is 19. There's 19 distinct objects. Okay, that's the size of that set. All right, and this is number 33. Yes, book agrees. Okay, good. All right, and 33. Let's go to 35. We're gonna do 35 and 37. And then the next part, D, this is gonna be the end of 1.1. We're gonna do that next time because it's sketching in the XY plane, and so that's gonna be a little bit different. And this is the other thing. I'm gonna be doing things again. I'm doing this as much for myself as for you guys, but I'm gonna show you how we do this in math class. Meaning that I'm not just gonna just like sketch this out on the screen. We're gonna use software. I'm gonna show you LaTeX and things like that. We're gonna do this not just how we do in math class. See, the thing what we're doing here is this is leisure. This is something that I'm doing because I enjoy it. This is fun time for me. So I really get to breathe deep and enjoy this book and take the time to do it, because one of the most frustrating things about math is that you don't get enough time to really soak in the stuff and just really marinate in it and take your time and memorize all this stuff. No, it's always go go go. You got to get through the semester, which yeah, obviously, because the whole point is to get you through all that stuff to where you have a working knowledge. You won't have a master, but just a working knowledge. You go to the workforce, you learn on the job a specific set of techniques that you will be using, and you just kind of operate there, and you'll learn more job related things. That's how you produce effective workers. But with me, I'm pursuing both things, both the education part, and I am pursuing trade. So I'm a professional landscaper slash handyman. And the thing is, as I mentioned in previous streams, if you go on my LinkedIn, I attended this thing for JP Morgan where I mean, it was a really good thing. But I could have gotten, or at least applied for, and possibly even gotten into the internship. Would have been a paid internship, but I would have had to give up all of the other stuff I had going for me. I would have had to just focus strictly education, and then get into this thing, and then stay on this track, and then work for JP Morgan, make good money. But the thing is, I was already making good money, right? The thing that a lot of people don't realize is just how lucrative trade can be if you get into it. And for me, I push everything simultaneously, and just some things I happen to be in the market to where, over the many years of me doing trades, I've built up enough of a working knowledge. And then last year, I've connected with some very high level tradesmen who ended up using me for every job they didn't feel like doing. I would take any job they would give me, anything. I don't care how dirty, how miserable, how tedious. I was the guy you go to. If you didn't want to do it, I would happily do it. And that enabled me to develop a kind of efficiency and quality to my work, and which, like even from skating, it's just like that kind of drive, the focus on detail, all that stuff I continue to use to this day. Anyway, so I'm a successful tradesman. I really enjoy this stuff, and I really enjoy math too. And it's just like I am, I guess, an embarrassment of riches right now with all the opportunities I have. But anyway, this is the kind of stuff that I get to enjoy right now and marinate in the math stuff. But let's finish up the last of these two questions, and then that will be it for today. All right, we have 33, 35. Okay, I'm just going to write it out first real quick, and then we're going to see what this wants. All right. Wait a minute. I just did that one. Okay. So there's just one more left then. Wait a minute. Make sure I did that. No, wait a minute. Wait a minute. Oh, no, I didn't do this one. It's just this like tweak on the previous one. That's what threw me off. Right. Okay. That works too. Yeah. Okay. So let's look at this for a minute. Oh, we just read it. We want to know the cardinality of this equation. So two things. We need to understand the equation, and then we need to understand how many distinct items the equation spits out, right? So let's read it. We want to know the cardinality of the set where x contains integers such that x squared is less than 10. All right. So then now we are talking about integers. So that's positive, negative, 0. Well, let's start in the middle. We'll take the 0. 0 squared is less than 10. That's true because 0 squared is 0. So we're going to say 0's in the set. All right. 1 squared is 1. 1 is in the set. 2 squared is 4 in the set. 3 squared. I'm writing this wrong. 1. We just want to know the ones there. 2 squared is 4, less than 10. 3 squared is 9. And that's the last one that's going to be on this end. And then the negatives are also exactly the same. Negative 3 squared is positive 9. You square anything, you're going to get a positive number out of it. So basically, this is our set that this equation spits out. All right. And then how many items we have? 1, 2, 3, 4, 5, 6, 7. All right. So the cardinality is 7. There are 7 distinct items. And hold on. All right. Did I do something wrong here? Okay. I solved it correctly, but that's okay. I solved it correctly, but that's not the equation. That's not the equation in the book. So that's what threw me off. I sometimes when I write quickly, and especially if it's a similar equation, you just pull from the line. Wait a minute. No. Hold on. No. Okay. I'm fine. Everything's correct. I'm jumping around. Yeah. Number 35 is 7. The 33, 35, and 37 are so closely written and that they're almost the same thing. So let's just jump down to 37, okay? So yeah, this is correct. That's fine. 37, again, things look almost identical. Okay, X contains naturals. So this time we're using natural numbers, and then we're going to say such that X squared is less than 0. All right, what? So we want to know the cardinality of this equation, right? Just like before. We're going to say X contains naturals. So naturals go 1, 2, 3, 4. This is the natural set, right? We know that. I'm sorry I write chicken scratch. I know. But anyway, if we take the lowest one in the set, 1, and we square that, 1, that's the lowest possible number. Anything above that, 2 squared equals 4. Anyway, there is no number where in the natural set that gives you less than 0. It doesn't exist, right? So that means the result of this equation is going to be the empty set. And the cardinality here, and now here's the thing. If we set that the cardinality of the set, this right here, again, remember the rule, we scratch 1, then you get 1. So the cardinality here would be 1. But if it's just like this, which is equal to this, which is equal to a cardinality of this set equals 0. So cardinality of the empty set, that is going to be 0. So yeah, that's it. By the way, this might be a little confusing. We're gonna say, yeah. This is what I'm a little. I'm gonna erase that right there, just because it's not. I kind of did an implication there, and implication's written a little differently, but just kind of jumping ahead. If you want to say something implies, you write 3 lines. So like this. That means implies. Okay, but we don't worry about that right now. Getting back to the question, 37. Let's read it one more time. What is the cardinality of this equation? Cardinality means the size of, in this case, how many items does it spit out? We count the items. That's the cardinality. X contains naturals. We know that naturals start with 1 and they go on forever. And we know that if you square anything gives you positive, but moreover, squaring the lowest number in the natural set, 1, gives you 1. And the equation wants less than 0. There is no number that's less than 0, resulting in the empty set. And the cardinality of an empty set by itself, not the set of an empty set, but just an empty set, is 0. There is nothing there. And yep, the book agrees. All right, that was fun. So I hope you guys enjoyed it, and I will see you next time. Thank you so much.